Uh, Hi friends, welcome back to the series of lectures where we solve problems from the subject of mechanics of materials. In this problem, we have a elastic straight bar of a given length. It is of square cross section. What we do in here is we have a straight beam as shown over here. Now we bend it in such a way that both ends meet. And finally it forms a circle as shown over here. A pretty real life problem, isn't it? We may have done this sometime in our lives, because we would have taken something straight and then we would have bent it into a circle. uh, just slightly digressing, I would say this problem is originally taken from the book of Timoshenko on mechanics of materials. The chapter on beam bending starts with a similar example where he explains all the concepts that goes into solving this problem. So I encourage everyone to read his books. That's one reason why I don't post theoretical videos on YouTube, because I still consider the best way to understand theory is to read textbook rather than watching any online videos. So let's start solving the problem. Here, everything is given. We have the length of the beam, we have the cross sectional details of the beam, we have the material properties of the beam as well. In the question itself, they are asking us, or they are telling us, we can invoke the Euler-Bernoulli beam theory. One of the key assumptions that goes into Euler-Bernoulli beam theory is that the plane sections remain plane and plane sections are perpendicular to the axis. They remain perpendicular to the axis. This is a key theory or a key assumption that we should always remember whenever people coin the word Euler-Bernoulli beam theory. Now, to describe the same thing with a figure, apologies for my chicken scratch. Uh, this is the beam in its deflected shape. I'm considering a scenario of pure bending. Pure bending means there are no shear loads acting. The whole beam across the length is subjected to only bending moment, not shear force. From a I'm not getting into the details of deriving all these expressions, but from a simply kinematic perspective, we can arrive at an expression for the axial strains for in a given section. So what I'm trying to do is I'm taking a section somewhere over here. I will draw it in detail. So this is the section of our interest. We have our x-axis going like this, and then this is the direction along which our y is pointing. So this is the section of our interest. So this is the section of our interest. Now I am trying to answer the question how axial strains vary across that cross section. No, so this is the expression. What it tells is we have a tensile strain. We have the strain profile going something like this, where here it is tensile, and where on the top we have compressive strains, compressive axial strains. Nothing great. This is all acceptable. This all comes from kinematics. There is no material model used in here for the time being. Now you know the strain profile. The stress is easy to arrive at, because we assume the material obeys Hooke's law and it is linear. Then the stress is Young's modulus times the strain. Fairly easy. Now you may be wondering, because I didn't explain you what rho is. So rho is the radius of curvature. I didn't explain. I should have explained it a little bit earlier, but don't worry. I will explain it fully. So this is the radius of curvature that I'm talking about. If we take a particular section, it is part of a circle. It's part of a circle. If you had something like this, a very straight beam, then your radius of curvature is infinity. But once you put a bending moment on the structure, the beam deforms, and each section will have a definite value for the radius of curvature. It may change from point to point, but assume that a particular section has a radius of curvature rho, then this is how the axial strain at that section vary with respect to your y coordinate. Make sense? Fine. This quantity, there is something called curvature as well. Curvature is nothing but the reciprocal of the radius of curvature. Some textbooks use the symbol kappa to denote the curvature. Now I have my axial stress as a function of my material parameter and rho, which tells me how much my beam has bent, or it is a radius of curvature. If the beam bends more, rho is more. Now just think of the problem that we have in our hand. What will be uh, the curvature or the radius of curvature of our beam? I will post my video so that all of you can think about it for a while and then come back with an answer. So this is the final configuration after bending. So the radius of curvature here is rather simple. If this is inside is Ri and the outside radius is Ro, what should be the radius of curvature that we need to plug into this expression? It's neither Ri nor Ro. This rho tells us the radius of curvature of the neutral axis. Have a close look at this figure again. Rho is the radius of curvature of the neutral axis, not the top plane or the bottom plane. This is something we need to keep in mind when we do this kind of problems. So in this example, the rho will be R0 plus Ri divided by 2. Makes sense? Because that's where the neutral axis lies in this particular problem. Neutral axis may not always go through the center. There are exceptions, but for this problem where everything is homogeneous, the neutral axis passes through the center. Now I think we have all the tools in place. Rest is simply plugging those values and evaluating the maximum stress that is acting in this bent beam. Where it will be acting, whether it will be acting at the OD side or the ID side. Think about it. Here what I have shown is a simple thing. It's nothing great. You know you had a bar of length capital L initially. If you bend it into a complete circle, something like this, the capital L, which is the length, that remains constant, but now the L can be written as the perimeter of this particular shape. Make sense? So radius of curvature can be evaluated in this manner. Once you know the radius of curvature, you can evaluate the axial stress, the maximum axial stress in this manner. Just plug and check, but always remember to use consistent units so that you get a sensible answer at the end of the day. So this is the maximum stress that comes out when you take a long bar of this dimension and then bend it into a circle. Make sense? So thanks for watching.